Okay. So, my name is Bhupender, and I'm an HPC architect at Mount Sinai School of Medicine. So, I'm not sure if you've heard of Mount Sinai, but it is one of the largest healthcare providers in the state of New York. It's actually one of the top employers. Employs about 40,000 people, and it's always been in the top five employers in the state of New York. What most people don't know is apart from a lot of a big footprint on the clinical side of things, their hospitals, they also have a big footprint in the School of Medicine, which is where they run their primary research activities. So, what I'll briefly discuss in this talk is the research that happens in the School of Medicine and also the workflow that they run there specific to a bioinformatics workflow. I'll go in a little bit detail into the systems that we have and the storage that we have been able to provide and discuss some of the issues that we've had and some of the resilience and maybe get some feedback from some of the folks and share our experiences in general about running the bioinformatics HPC cluster. So this year Sinai is celebrating 50 years, and you can read all about it on a Scientific American blog that they specifically put up for this. And for a long time, Sinai's focus was on clinical activities. So they were exemplary in the field of clinical trials and doing things that help, like the procedures and stuff. And they were slightly falling behind in terms of the upcoming research in big data, especially. So, 10 years back, when they looked at their next 10-year plan, they wanted to invest heavily, and HPC was one of the core areas. So, that's when the initiative started. And we spun up the HPC. I wasn't there, but a couple of leads who had a very good experience, we should go with, they came in and they were able to kickstart a project and an initiative that has since led to a lot of useful research that's being done here. So this is just to give you the footprint of research that happens in the School of Medicine, and you'll see there's not just one traditional department. You know, traditionally in the school you have the physics department, the sciences, the engineering. This is all medical sciences. This is all the departments are genetics, neurology, and then we have these big centers of excellence that carry a lot of useful research that have a direct impact on what is happening to the patients. So this is the kind of research data that flows in and out of our school and in and out of any other medical school. This is pretty emblematic of the research that happens here. We used to be a big data center shop with everything inside, and most medical facilities, actually, to generalize, there are two groups that might not have moved to cloud as much as others, and those two groups at this point are medical universities and companies, and maybe finance companies, because they have to protect their data more than anyone else, and it has consequences. You can get penalized heavily if your data is found somewhere else, and that comes from straight HIPAA guidelines that FDA has in place. So, but as we look and move towards larger systems, larger sequencing machines, we see that we are getting in data from all sorts of places at a much higher rate. Just last month, I got 6 snowballs given to me to hook up to our network to get all the data. A very frequent rate, I get NAS disks that need to bring in data because the network is simply unable to keep up between two very distant geographic locations. So what we are seeing now is people trying to avoid the network cost, not just the storage cost, but also the network cost to get the data to a place where they can have it close to a compute. In Sinai, it generates a lot of its own data. So at some point, we have to have a good footprint, within our data centers because we can't be too far away from those machines that sequence all of the data. Sinai is a very interesting project called BioMe, for instance. It's a big biobank, a research initiative which has 40,000 people enrolled in it. And what happens frequently is if you go out during lunch, they will give out freebies for those who are willing to let their blood be sampled and DNA be sequenced for research purposes. And that goes into a biobank where Sinai can look at that data and do some other research for that so they can tie in the cases coming in for instance, cancer and other activities, and be able to say that there is a pattern here, and they're able to look at diseases and say there is a pattern here, and we can tie it to a certain variation in the mutation or in the genes, and they can do further research on it. So why am I here at the DDN booth? And that's important because we've been using a DDN system that we had received as part of a grant, and that system has been very useful for us. So as this grant comes to close, we would like to summarize it and provide our feedback on how it has worked out for us, and I'll show you some numbers that will clearly tell you what we've been able to achieve. And second is just to share our general experience around GPFS that we use very heavily. We have a project-based file system, and most sites for project-based file systems who want a parallel file system are doing GPFS. A lot more sites are doing Lustre for scratch storage. But when it comes to keeping some sort of policies in place, your quotas in place, then GPFS at this point is still way ahead of the league. And our usage when we first started has gone up gradually. You might see a little dip there in 2018. That's where we started charging for storage. But despite that little charge, it kicked up back again. So we have around 250 projects which use our project space. And despite the charge, they need it. The data used to be in the order of a few gigabytes and maybe a terabyte. Now the files are getting larger, and a lot more files are coming in straight from sequencers internally and from the other data sources outside of Sinai. This is just our distribution. The projects are evenly distributed between departments and so on. We don't have a big footprint of data from outside of our data sets. The job mix is another very interesting aspect. If you look at the job mix, most of the jobs are single slot jobs, and this is very peculiar about bioinformatics. Most of these jobs are single slot jobs and run less than an hour. A lot of them run for maybe a few minutes at most. And if you look at the kind of applications they run, you will see very little MPI. In fact, we have maybe 20-25% footprint of MPI parallel jobs, but most of our jobs are single slot jobs, big task arrays that need to run at the same time, and they have different demands for scheduler as opposed to the other workflows. This also creates a lot more metadata. When you have tasks that run for a minute and create 10-20 files for the task, then you have a different ask that you're asking of your file system, and for that reason also we've been happy with the GPFS at this point. To mitigate some of the other issues around performance, we've always kept our metadata on flash. That's been one thing that saved us throughout by having good performance, and we have different tiers that I can discuss that we deploy to our file system. In general, we've had experience with a lot of ESS solutions, with GSS solutions and DDNs, and this is a slide that I wanted to put in just to summarize a few differences. In general, we have what is direct attached JBOD solutions, where you have a few servers and everything is attached directly via SaaS connections. And we have solutions that have servers but talking via controllers to storage arrays. And that's one example of a DDN solution which is controller based. And what we've come to see is you can put in a lot of, or you can get a lot of capacity when you have direct attached JBoards. When it comes to stability, the controllers do help a lot. And, in fact, in our system, we've had to open very few hardware issues to get it to work, and the upgrade process, aside from getting the firmware on the controllers, is at GPFS level pretty easy step. It's become a lot more complicated to push your storage up to newer levels, but with GPFS and lacking some of the other proprietary bundles of software, it's been a little easier. So this has been our path, and we are slightly different from rest of the community here. We have a single GPFS file system that we use to provide storage at this point, and this file system has grown to be about 13 petabytes. We started with DDN 10K. We were one of the earliest consumers, and we moved to DDN 12K, and that's the project that's coming to a close. That was out of an NIH grant, and it's been very, very stable for us. And all of these resources have gone into a single shared file system where we've brought in one out and rotated the other ones out. And keeping one file system up takes a lot of work. These are some of the details for our GPFS configuration if you are interested in the technical details. But essentially, what you will notice is we have a big inode footprint. We have about 2 billion inodes in the file system. And 4K is the size of the inodes. That helped us put in a lot of the tiny metadata and the data into the inodes itself. So a lot of the access is very fast for a lot of the small files that we have. And we've been able to roll into the most stable GPFS version in years and be able to bring everything to a level where we're very happy with the performance. So this is a little more detail for those who might have interest in it. We've seen different storage pools come in. In GPFS, you have pools, and we've been able to rotate newer pools in and take older pools out. And this is the sort of facility that makes GPFS useful for us, where you can bring in a storage, be able to take out different pieces, take out hardware that you like from vendors like DDN or other vendors, and be able to say that this works for me better. I want to have this in my particular storage pool for this set of customers, for which the cost might be a better way of looking at things as opposed to performance. So this is something that that's been useful to us. These are more details on how we moved like 4 petabytes of data over several weeks in rotating out 2 of our oldest clusters. But these are details you would be interested only if you're running such a solution in your data centers. So to summarize, the kind of activities or achievements we've been able to make by employing this grant, we've had this DDN solution. The amount of publications that came out of it and the utilization that came out of it was enormous. I've worked at other sites where if you could get 10 publications, good ones, out of a proposal, it was considered an achievement. We've been able to get over 100 publications during this time, and some of those publications have been really great, featured in Nature and Science. So the amount of scientific research and the activity that it has generated has been immense, and for that reason I'm here to summarize how useful this project has been. There are many challenges in the system and the setup that we have in particular, and having a single file system and not being able to focus all your activities around it just brings in some more challenges that you might not have, but at the same time it also makes it very easy for your users to have a simpler understanding of the charge policies, their quotas, and their planning of data management that goes into a project-based file system, especially when you start charging them. And we have immediate challenges, and these challenges are specific, some of them to the medical community, and those all revolve around the data security and compliance that you have in place. And for those, uh, we have a different set of needs, and we are looking at different solutions. But as always, we'll be looking at what provides the most stability and the best value to our users. That's essentially what I wanted to share with you guys. And if you have any questions, you can just talk to me about it.